Hello, everyone. My name is Alex Turner, a program manager on the Managed Languages team at Microsoft. And we worked on, really for the last 2 years, preparing for Visual Studio 2012, was this async support. We also did Windows runtime support, but our key kind of language feature has been async. And we've talked a lot about how you use async in terms of building awesome responsive apps. Right? And you've seen other sessions here. There's been sessions about how you use async with ASP.NET, right? How you write server apps that take a big dependency on async to give you that scalability that you're looking for. And so, we've had a lot of talking about async in general, but not really so much specifically about you as the library author, right? Somebody who actually either sort of within your company wants to write libraries that other teams are going to use, right? If you're kind of the senior dev and you want to produce these kind of libraries, or if you're somebody who actually ships libraries to your customers, right? If you're creating libraries that give asynchronous access to your services or so on, what those best practices are around producing this type of async library. And so what this talk is about is those best practices that we've learned from talking to customers over the last 8 months or so since we've launched to figure out what are those things that people do that potentially hurt their scalability, hurt their performance, and potentially make assumptions, right, as a library author about what your consumers are going to do. As an app author, you're in a much better place to take a look at the whole system. And you can do performance tests, you can find those bottlenecks. As a library author, you do have to be a bit more defensive because you don't know all the ways in which your library might be used. And you want people to be able to use your libraries from UI code, from server code, from the UI thread or from background threads. And you want all of these to work just as well, even if you're kind of focusing your testing on one or the other. And so I guess how many of you out there have kind of either seen talk about async before, or have played with async, the await keyword, yourself? Good. OK, most of you. So this talk, we're going to be kind of having a very quick intro, or sort of talking again about our definitions for what we call async, what we call synchronous and asynchronous methods and such. But this is going to assume that you do have some knowledge of the async support that we're putting into the language, right? This is really going to that next level to figure out what does it mean not just to write apps, but to write libraries. And so what's important to figure out is sort of what these definitions are, right? We've talked about what synchronous and asynchronous methods are, but there's actually a few more terms that we're going to start using, sort of sync over async over sync, that become relevant when you are thinking about libraries, especially if you're somebody who's kind of wrapping some existing libraries that you have. And so that first thing we want to talk about is really what does asynchrony mean, right? It's kind of an overloaded term. It can mean things where between multi-threading or multiplexing on a UI thread to sending work to background threads. So what do we actually mean when we're going to talk about asynchrony? Well, when you have something that's synchronous, when you actually have a synchronous contract that you, as a library author, expose to your callers, something like a foo method, right? The idea is that this is something that's going to be performed here and now. Somebody who calls this method expects that this action is going to be performed right now on that thread, and that they're not going to actually get control of their thread back until that operation is complete. It's going to block until that operation is done. When you expose an async method, you have foo async, your caller expects something different. They expect that calling that method is going to kick off the operation, it's going to initiate it. But then they expect that they're going to get control of their thread back right away. Right? And they're going to be able to then go on and do something else. They can execute other things. They can potentially call your method again and try to parallelize by multiplexing on that one thread they're using. And they expect they're going to be able to do other things there. So the key, though, is that the way that people invoke your method, this contract you expose, actually doesn't necessarily tie to the way that you implement your method internally, right? Like, you might have a synchronous implementation, and there's tricks you can do to wrap that and then expose it as an async method. You might just shove that synchronous method off to a background thread, and that's probably sort of the most tempting way to go about exposing an asynchronous API if you already have a synchronous API, right? And so your callers are going to try to make assumptions about how your methods work by looking, is it async, is it sync? And it's up to you to make sure that those assumptions are kind of valid, because they can't actually prove that all the way through. They don't have your code, right? And so you want to make sure that you're not kind of fooling them at their layer, and we're going to talk more about that. So let's just look at one example. So sort of sync versus async. We have some simple method we want to write. It's going to pause for 10 seconds and then output hello to the console. So if you have the synchronous version of this, don't actually write code like this. Don't do that. That's not the way to wait 10 seconds, but you can imagine waiting 10 seconds like that. You set an end time, and you just keep looping forever. You spin until 10 seconds have elapsed. So that's one way to do it. Asynchronously, though, you might say, all right, well, I have this synchronous method. I want to expose an asynchronous method. I heard asynchronous methods are cool, so I'm going to go write pause print async, right? And maybe you're going to say, okay, threadpool.queueUserWorkItem, right? This is a method that's been around forever. It does what it says on the tin. It queues a user work item into the thread pool. We're going to say, all right, fine, pause print here, and we're going to call it. This is going to be something that goes off, runs on a background thread once there's a thread pool thread available for it. Now, what we'd prefer you write these days is task.run. You see, actually, the previous one, it returned void, so there's no way for the person who calls it to know when that work is done. We now have task.run, which similarly puts stuff on the thread pool. It's shorter, because we expect you to write this pretty often these days. But it also returns a task, right? And so you can return that task to your caller, and they can keep track of when that task, when that background work is actually complete. And this is an example of what we're going to call async over sync. Right? You have a core synchronous implementation. It's actually going to sit there and burn the CPU until 10 seconds have elapsed. So that's the core bit of CPU work that we're going to do. And this is going to present an async sort of veneer over that, right? You're creating a facade that, oh, I'm going to call this and it's going to go off and do some stuff. I don't have to think about it. You've created this sort of nice abstraction and people don't have to deal with that. All right, well, we can do that. But it's not necessarily truthful to the user, and we'll see some of the assumptions later that the user is going to make about asynchronous methods that are violated when you write code like that. Well, you can also have the reverse, right? Let's say you actually have some asynchronous implementation. You've started this API in .NET 4.5. You've written some code, like this, that's going to go off and kind of wrap hello. You're going to use a timer to say, all right, after 10 seconds have elapsed, go ahead, use this kind of task completion source trick to rig up a task that's going to complete once that's done. And so you go ahead and do that. That's fine. So now you have an async API. But you don't actually have to write all of that code to do a timer. So we actually have task.delay, which gives you a task that waits 10 seconds. So we've already done that kind of work for you, right? And you could just await that, and that's the same thing. So you might write code like this. Assuming you have that async API, but now you feel like, well, I have a foo async method here. I just want the foo method. I want that pause print method, that synchronous one, in case someone doesn't care about async right now. So you might be tempted to implement this, right? So pause print, just take the pause print async method, take that task that I get back, and call .wait on it, right? And .wait is that method that lets you synchronously block on a task that you have. So you could write this. And if you wrote this, somebody could be calling you from the console, call pause print. It'll block for 10 seconds. It'll output this. Maybe that's what they want. And what this is an example of is called sort of sync over async, right? That's what we're going to call it, where you have an actual core async implementation that really is async, and I'm presenting this synchronous veneer over it. I'm doing the work for the user of calling .wait on that. And so you could potentially see this as a convenience also. But both of these cases where you're kind of wrapping like either a truly synchronous or truly asynchronous implementation with the other kind of method, both of these can be problematic if you're not really sure exactly what's going on under the covers, either in the methods that you're calling or in sort of the plumbing of async itself, right? And similarly, your callers, when they're calling you, they're going to make assumptions about what they can do with your code. And we're going to see some of the problems that result from rigging up these kind of impromptu kind of sync and async methods and what the best practices are. So why are we bothering to go async in the first place? One thing that's important to realize is that there are actually pretty discrete, different reasons why you might want to use asynchrony. And at times, they can actually be at odds with each other. And so one core reason you want to be asynchronous, sort of in the general sense, is offloading, right? So it means one of two things. Either you don't want to tie up the current thread you're on with the work you're doing. Like, so for example, I have some work. I'm on the UI thread. I want to do some CPU-bound work. I can't be doing that on the CPU. I need to go off and do that somewhere else. I'm sorry, on the UI thread. I need to go off and do that somewhere else. I need to do it on a background thread, right? So I'm going to avoid tying up this special thread. Some threads, like the UI thread and XAML apps, are special, and they have special privileges, and there's only one of them, right? And you don't want to block it. So that means some threads matter more than others. I might want to push this work off. At the same time, I might actually just want to do work on a specific thread. Let's say I'm on a background thread, and I need to go manipulate some buttons in the UI. Well, I have the reverse, right? I need to actually do work on a specific thread. And so you'll use things like dispatcher.invoke to go schedule some work on the UI thread. And so you're kind of offloading in either direction there. And that's one reason to use some of these async constructs. The other one is concurrency, right? So I might have multiple operations that I want to perform at the same time, right? And so that could be either me kicking off a bunch of background threads if I actually have CPU work to do, calling task.run a bunch of times. It could be me just trying to multiplex on the UI thread. I want to kick off 1,000 downloads, but I want to come back to the UI thread after each one so I can update the UI, right? And so if I want to do multiple things, I need some of these async constructs to actually pull that off. And kind of the other reason to go async, and we're putting this line here to kind of distinguish, you'll see why in a sec, is scalability. And scalability is about not wasting resources, right? And one of those resources that you want to conserve is threads. So let's say you're on a server and you want to handle as many requests as possible, thousands of requests per server. If you want to do that well, you better make sure that you're conserving all the resources that could become bottlenecks. One of them is the memory and the thread switching cost associated with having a lot of threads running on the machine. And let's say you have a server that can handle 2,000 threads. If you have one request per thread, you might be able to handle 2,000 incoming requests at the same time. Maybe if they take a second to process, you can handle 2,000 requests a second or something. If you're going to then go consume 2 threads per request, you're then potentially limiting your scalability. You're going to maybe even cut it in half. You can only handle 1,000 users then because you don't have as many threads to grow into. You really want to limit yourself to that 1 request per thread, or 1 thread per request. And so what matters here is how useful this idea of async over sync can be for these different scenarios, right? So if I'm offloading, right, I want to take this method that I've got. I want to run it on a background thread. Well, that's the perfect case for async over sync, right? I call task.run, I take my method, it shoves off to a background thread. That's great. You should all do that and keep doing that, right? But let's say that I'm caring about concurrency. I want to actually kick off multiple operations here. Well, task.run and parallel.for can be useful, but they're potentially only useful if you actually have CPU-bound work, right? I don't necessarily want to be using some of these constructs and shoving things off to threads and changing what thread I'm on. I might actually just want to stay on the current thread and not burn other threads, right, if I actually want to get the maximum concurrency for things like network downloads, right? And so it's not necessarily always valuable for concurrency to be using these async over sync patterns, especially in your libraries where you're sort of forcing the hand of the app developer. And then on the flip side, for scalability, async over sync really doesn't help you for scalability, and it can actually hurt you, right? If you are using task.run to say, I want to do 10 downloads, I'm just going to spin up 10 threads. Even if you do async work on those threads, right, you're still having cases where you're doing a lot of thread switching. You're still spinning up all of these threads, and there's going to be times when there's contention. You're going to use way more threads per request. And at that point, you're potentially limiting your scalability, right? And it's one thing if you're the one writing the app, right? If you're the one who's actually building this out yourself, that's fine. You can do your performance tests, see if you have the performance you need. But as a library author, you have to make sure your library is general purpose. You might be testing your library in a UI app, but the people consuming your library might be using it on a server, right? And even within your company, within your own organization, you might have some useful helper functions you write. You want to be thinking in this kind of way to say, well, hey, if right now I'm writing a Windows Store app, and later on I'm going to be writing some app on the server, some ASP.NET MVC thing, and I'm going to go off and I'm going to use this method to do some similar kind of processing. You don't want to have to rewrite that or re-performance test it. You want to be following these kind of best practices we're going to go over to help you operate well in all of these environments. And so you want to think about these different APIs that you can call here. So task.run, great for offloading. That's basically what it's for. Sometimes great for concurrency, right? And parallel.for, right? That's something that you can use for this kind of concurrent work when you're doing a bunch of concurrent CPU-bound, heavy lifting kind of processing work. But you don't want to use it when you're doing I/O-bound work. At the same time, right, both of those things, both task.run and parallel.for, those things are not useful, right, when you're looking for scalability. You don't want to be spinning up lots of threads to handle that kind of stuff. Even if you're doing CPU-bound work, if you care about scalability more than kind of response time or latency, you should probably just do that stuff in serial. It's all going to be crunching the same CPU cores. Just do it all in a row, right? Handle as many requests as you can. But what you do care about if you're not doing CPU work, if you're doing I/O, you want to multiplex that one request thread you've got, right? And so you want to do asynchronous I/O, and that's where the key is for getting scalability. And so the key to remember is that async and await as keywords are not about kind of going async. Just putting them on doesn't make things async, right? It doesn't get you any of these qualities by itself. They're about composing these asynchronous constructs that you're calling into, the download methods you're calling APIs like task.run and being able to await it so you can compose over all of these different background threads or the background work that you're kicking off, right? And similarly, you're going to be composed, right? The library that you produce is going to be used by other people. And so you want to make sure that you're a good citizen on their platform. And so the key to this is sort of library thinking, right? Even if you've kind of been using async and you've been comfortable with it in an app, there's some principles that we want to kind of establish now about what it means to be a good library thinker, a good citizen of the general .NET Async platform so everyone can call you and benefit. So kind of the first step, we're going to have 3 core principles here. The first one around being a responsible library developer is that library methods shouldn't lie. And there's 2 things we really mean by this, right? One of them is if I'm defining an asynchronous method, I should be honest, right? I should only define that asynchronous method if, and only if, right, that method is not going to be thread-bound, if it's not going to start spinning up new threads in the background. People have an assumption about what an async method means. They think it's going to not create new threads, and they think it's just going to make very good use of the thread that I'm on. The other principle is that if I'm going to make a synchronous method, if I'm going to expose like a foo method, be honest there too, right? Do that only if you actually have a synchronous implementation, if you actually have some better synchronous version that somebody should call, right, versus just awaiting or even blocking on your asynchronous implementation themselves. Right? Use that suffix, use the nature of the method that you're defining to help people understand how your implementation works. Don't kind of abstract too heavily to where they're going to make the wrong assumptions. So let's look at each of these in turn, right? So for async methods, what are the assumptions people are going to make? So some consumer is going to come up to your library. They're going to read a bit of your documentation, maybe, maybe not, look at the XML doc comments, and they're going to see, hey, here's a method. Its name ends with async. So, well, if maybe I'm in a server app, well, I bet this method's not going to spawn off new threads because I was going to spawn them myself if I wanted them. So I can trust this method to be a good citizen on my server and not kick off new threads. I also know that I can parallelize this. Hey, maybe this is a download API. Hey, I want to kick off 100 downloads. Well, I'm just going to call this method 100 times, right? Because it's giving me back tasks. I'm just going to call it 100 times when all and all the tasks. I'm good to go, right? And it's not going to actually be hurting my scalability there to do so. So these are the core assumptions people make when they see async on the end of your library method. So the question is this actually true for the asynchronous methods that you're creating? So what we're going to do is we're going to take a look at what happens when perhaps this isn't actually true for what you're pulling off here. So I'm going to switch over to VS, and I have a simple demo app here. We're going to go through a few different examples over the course of this demo, over the course of the presentation. The first one is going to be around this idea of sort of async versus task.run, how this async over sync stuff works. So if I go in here, you see I just have a simple app. This is a console app that I'm running in here, but I'm just spinning up a simple UI. Like you see I'm spinning up WinForms here. This is sort of the minimal code I need to just get like a WinForms form up there with a button. The point of this is to get me an actual UI thread. Right? I want a UI thread so I can operate against it, but I don't want all the rest of the plumbing right now because we're just trying to isolate this effect here. So I make myself a new UI app here. Here's my click event on the UI thread. And this is the app code, right? Actually, before we look at that, let's take a look at what you've written as a library author. You're exposing this library to anyone, right? And you expose it as, let's say, fetch file async. And you might have some of these different I/O methods here in the background. Maybe you have a download file method and a download file async method, right? And we're going to kind of simulate download file, right? So the synchronous download file method, this API call we're calling, right? We're going to call that thread.sleep, right? So it's just going to sleep for 1,000 milliseconds. It's not going to burn the CPU, but it is going to actually block that thread for 1,000 milliseconds, which is how I/O behaves. And download file async, right? Now the asynchronous version of this, we're going to return task of string, and I'm going to here do that by awaiting task.delay. That's that helper that just yields the thread for 1,000 milliseconds. It's going to come back and take that thread back over once it's done. And so this is going to let me simulate an asynchronous file download. Again, I don't use the CPU, but here I'm also not using the thread. And so let's say that, well, I'm calling this download file method. Maybe it's actually the only method that's available. So I'm saying, all right, I have my fetch file implementation. Maybe it actually looked like this. And so I'm going to wrap that with await task.run. And I'm saying here, cool, now I can take this code that I have, I can make an asynchronous version of it, I can return it. This here is me doing async over sync. I have some core synchronous implementation that would block the thread it's on, but I'm going to spin up a background thread. And that way I'm going to go block some thread the user doesn't care about. And OK, so cool, I'm doing that. Now up here in the application code, this is what my app author might write. Let's say they want to call into me, they want to be asynchronous. This would actually keep them responsive, because it does go off and kick off background threads. But what if they instead don't want to just do one of those? They want to actually call it 100 times. Right? They want to go download 100 different files. They're going to go here and say, all right, make a for loop, get the file number, kind of pass it off to my library method I defined, and add each of those tasks that comes back from the async method into a list. Right? And then I'm going to go await all the tasks. Do a when all to say, hey, hold on until all of those tasks are ready, and then come back. It's just going to make sure they're all kicked off, and I'm paused waiting on them. All right, well, if a user goes to write this, let's actually move this here, and I'll click Run. And we'll see as we go through, we've kicked off all 100 of these tasks. But unfortunately, since each one wants to go pull up a background thread, you see they're actually going in bursts, right? When I kicked off this, I have 4 logical cores on this laptop. And so I had 4 threads. The thread pool starts off saying, well, you're doing CPU work, we expect. We're going to give you as many threads as you have cores. And so it gives me 4 threads. But then it looks a second later, and it says, well, you made kind of crappy use of these threads, because most of the time the threads were idle, waiting on I/O. So it looks like you must need more threads. And so over time, right, you can even do that again. Over time, as I was clicking through here, we saw that, all right, well, maybe in the first batch is 4, and then maybe another 4, and then 5, and then 5, and then 8, right? It's kind of ramping up the number of threads that it's devoting to me each second as it observes me kind of wasting these threads it's given me, right? It says I need more and more and more, but the thread pool has this predefined scaling behavior. It uses this kind of hill climbing signal analysis to figure out whether it needs more or less threads over time. And so if I kick off my app here, I have to wait for the thread pool to kind of catch up with me. But I didn't really need any other threads. And as an app author, as somebody consuming the library that I just produced here, they didn't expect any threads were involved. They're sitting on a WinForms UI thread trying to do some async downloads. They looked like I had an async API, but suddenly I'm abusing their thread pool, right? And that's the key. You don't want to go messing with something that isn't yours, right? And one of those things is the thread pool that's in the user's app, right? They might be doing other work in the thread pool. They might actually have important CPU work they want to go schedule there. But if you're sort of stretching out their thread pool, you're putting work items in there just to do async downloads in the background, right? You're potentially abusing that, and you're changing the characteristics of their thread pool. And that could interfere with performance somewhere else in their app, because that thread pool is global. And so let's take a look now at what happens. Well, there actually is this asynchronous version I can call. So I'm going to get rid of all of this code, come back here, and I'm just going to call download file async. And I'm going to await it. Right? My method is already async, right? But now I'm actually calling the asynchronous versions. Now this is just pure async. There's no async over sync. There's no wrapping. I have an actual async API at the bottom. And so I run this again. I click my run method. And all 100 files can download at the same time, which is what we'd expect, right? They're all just network requests. My computer doesn't have to do anything. It's just my network stack sending out 100 requests. I shouldn't have to block waiting for my thread pool to grow and shrink. I just want to use my one thread I have, my UI thread, to kick this stuff off. That's my assumption as an app author consuming the library. And so you don't want to be a library author who violates that assumption. And that's the key lesson here. So inside your libraries, if you wrap synchronous things using task.run, you could then be putting roadblocks in that prevent the app from actually managing its threads effectively, right? You're kind of abusing that one shared resource. And so the key is to let your callers be the ones to call task.run. If they want to go put some synchronous thing off on a background thread, let them do that, right? You should actually expose something that looks like what your method really is. If you only had a synchronous way to do it, that's fine. Expose that synchronous way, but let them make that call about then, do I want to have one background thread that does this? Do I want to have a smaller pool that I keep isolated? Maybe they only want to run your method in some private thread pool so it doesn't abuse some other thread pool for kind of critical calculations, right? Let them make those calls about threading. You're not in the right position to make that call. And it's because the thread pool is this app global resource, right? All the APIs that are going to be calling task.run are going to be sharing that same thread pool. And it's going to be growing and shrinking in response to what you do. It's similar to the garbage collector, right? You want to be a good GC citizen in your API so you don't abuse and make a lot of garbage that's going to cause pauses elsewhere. It's the same with the thread pool. And in a server app, this was a client app here, but spinning up a bunch of threads hurts scalability, right? I don't want to abuse the thread pool there either because they might be counting on those other threads to be request threads and to handle incoming requests. And me wasting them on background downloads when I don't actually need to have those threads wasted is going to limit their scalability if that's what they care the most about. And because it's deep in this API that I'm defining, it's going to be a pain for them to go find that scalability bottleneck. It's not a mistake they made. It was a mistake for them to sort of trust my API. That was what it turned out to be. And so again, the app is really in the best position to manage its threads, and you should leave that up to the app, right? Provide synchronous methods and have them actually block the current thread when that's the core implementation you have. Provide asynchronous methods. That's great, but do so when you can do it without kicking off new threads, right? Let the user use their own domain knowledge of what they're building to know how they want to manage their threading strategy. So there's a few exceptions, right, as with everything, where that core principle doesn't apply, where there are exceptions to that. One of them is if you're defining a Windows runtime library, right? If I'm exposing a WinMD file and I want people from other projections, people to consume me if they're in JavaScript, let's say, or C++, well, exposing a WinMD file means that JavaScript caller might call me. That's probably why I'm doing it. And if I did that, well, JavaScript doesn't have built-in threading support, right? The reason that you'll see sort of even more async APIs in Windows runtime, maybe than elsewhere, is because of that. You need an ability for JavaScript to do these kind of long-running operations without blocking their core thread, which is their UI thread, right? And so you'll see in the Windows runtime methods that go and do basically image resizing or other things like that. But they're going to do so without having just a synchronous version. They're going to have an asynchronous version, even though that's CPU-bound work, right? And the reason they're going to do that is because of JavaScript, right? And so if you're exposing this to JavaScript and you expect your method's going to take more than 50 milliseconds, then go ahead and expose an async over sync method, right? That's the compromise you have to make because you're talking to other platforms, right, which can't do this kind of work, offloading themselves. So the one other core place where async over sync is okay is in a class hierarchy, right? And so in the framework, we have stream.readAsync. This was introduced in .NET 4.5. And stream.readAsync, it's an abstract method that's on that base stream type, and so other streams can override it. And in fact, they do. Network stream and file stream override that, and they provide good implementations to go do asynchronous I/O. But anybody can define a stream, right? And you might be talking to a .NET 4.0 stream that just was never updated to have asynchronous support. Or you might be talking to a stream that just by its nature is only synchronous. There's nothing else you can do there. And so in those cases, well, the only base implementation we can provide that's correct is to call task.run and go off to the background thread. So if you call read async and you have a stream that came in and it is a stream that doesn't know synchronous operations, then that's what you're going to get. So there's no choice there, but you expect that the good streams that you're going to talk to that know about asynchrony are going to do a better job there. And what's interesting is even memory stream can do a better job implementing read async than doing task.run. You might think, well, like a memory stream, that's a pretty synchronous thing. It's already there in memory. There's no I/O to do. I'm just kind of doing the copy. But you're doing these buffer copies anyway with file stream and network stream. The memory stream is going to be super quick. It's just copy the data from here to there, right? When I'm doing a read, it's going to copy it into a byte array and return it to you. And so if I'm doing that, well, that's fine. That's so quick, it's going to meet their expectations. If it happens in 1 millisecond, that's fine for an async API. And so they just implement memory stream.readAsync to block, to call read. And that's an OK thing to do. That's a place where async over sync is OK when you have an implementation that's so quick. But make sure when you have those ones that are quick, you just do it right there, right? It's fine because they just synchronously called it, even on the UI thread, because it's so fast. Don't call task.run. Don't spin up a thread when you have super quick work that you want to do in an async method. Just do it. And there's even to get even more perf, once you have these things that are so fast that people are going to use them a lot, you want to squeeze out even more performance, right? And memory stream has some cool examples there, which we're actually going to see towards the end of the talk. So, OK, well, that was async methods. Now, if you have synchronous methods, right, like you have standard methods, foo, right, and you have a foo async method, you might think, all right, well, I want to have a foo method. Not everybody's going to be using async methods. Not everybody's going to want to call me in this way. Why don't I just give them a helper, right, that does the same thing as this method but has a synchronous contract? So user sees that. A caller to your API, to your library, is going to see this synchronous method. They see, oh, man, all right, well, this method has an async and a sync method. So, well, I guess the sync version must be faster than the async version. Why else would they define it? Otherwise, I would just go call the async version, right? So it must be faster in some way. I guess I should use it. And also, if I'm on the UI thread, maybe I'm in some complicated code, or I'm in a catch block, or one of the few places where I can't await or something, and it's like, well, I know I don't have that much data here. I'm actually not going to the network. I'm loading from isolated storage or something. This is going to be quick enough. Maybe this is going to take like 5 or 10 milliseconds or something. That's fine by me. I know I'm already showing a progress indicator or something, whatever. This is fine. I'm just going to call it from the UI thread anyway. I know by my domain knowledge, I know that the latency is going to be fine, so I'm just going to call your synchronous method, even though there's the async one there. So these are things users are going to tell themselves, right, when they see that you have both a sync and an async method. And so does it make sense for you to expose foo if all you're going to do is call foo async.wait or foo async.result? So let's take a look. We're going to go back in, and we're actually going to look at a different app this time. We're going to look at let's see here. We're going to look at a Windows Store app. I'm going to switch over. And in this Windows Store app, it's a pretty simple app. It's just going to have a button, right? When you click the button, it's going to be calling this foo method that we've defined in our library. Oops. And the library we've defined, right, here is the method in question, right? So this is just a simple method. We're doing some dummy work here. We're saying await task.delay, but that means we have a truly asynchronous method here. It's going to free up its thread and be a good citizen. That's the true async method. And then let's say we have that method. It's going to do some work, but we also want to expose the foo method. We want to be nice and convenient for our users, so maybe we want to say foo as a synchronous method. All it does, right, there's no return value anyway, so I'm just going to say foo async.wait. That's fine. Just block until it happens. And if you're in a threading context where that makes sense, then you could go ahead and do that. And let's even say here, the user who's calling this might know, yeah, I tested this. It takes about 1 second to return. For my needs, for whatever reason, that's OK if I block the UI thread for 1 second. Let's just go for it. So the user calls library.foo. They're calling your synchronous method. Well, we run the app now. And if I click the button, I expect it's going to hang for 1 second, but then it'll recover, right? And so I click it, but actually now it's stuck, right? It's stuck, and the button is even stuck, kind of pushed in. It won't even pop back out because the UI thread is no longer pumping, right? It's for more than just 1 second. It's now permanent. If I actually leave this here, eventually Windows will get angry at me for being a bad Windows Store programmer and will actually close my app down forcibly, right? And so why did this happen? Like, why did this take more than 1 second? The user, knew that they had to make a compromise here. They knew that they had to, deal with the fact that the synchronous method is going to block their thread. They accepted that, but they didn't want a deadlock. Right? And that's what they got. And if you take a look why, you see that when we get into foo async, we're calling here, foo async is awaiting, right? And because we're still on the UI thread, what it's going to do is say, all right, wait 1 second, and when you're done, make sure that we're going to post this work back to the UI thread. That's what await does. It makes sure that your work goes back where you came from. It's very convenient for app authors, right? So it's going to go back where we started. But at the same time, immediately, once we kicked off this task, we came back to this method, and we called wait. And so we've now blocked the UI thread. And so the message pump is stopped, waiting for that signal that the thing is done. But that signal is going to be coming from some message that's queued later on the UI thread, right? We're posting back to the UI thread to actually then free up this task and tell it to continue. And so we've caused a deadlock. And we'll see more about this deadlock later. But this is the kind of situation your users can get into if you're exposing synchronous methods that aren't really synchronous, right? You're waiting on their threads, right? And you're kind of, in this case, again, abusing this kind of global contract, right? The user called a synchronous method. They didn't expect you to block their thread any longer than it takes you to perform their operation. But that's what you've ended up doing here. And so if you expose a synchronous method that calls wait or calls result on top of some async method that you have, you're just inviting deadlocks if apps decide to call you on the UI thread, right? And even if you say it's a bad principle or a bad practice for people to do that, and they really shouldn't do that, they're going to find occasions to do that, right? And you don't want to expose an API that leads to deadlocks. And so really the principle here is don't just expose synchronous methods because of symmetry, right? Because it's, look, I have an async method, I should probably have a non-async method. I see that everywhere, I should do that too. If there's a sync method, users are going to assume there's some good reason to call it. You must have defined it for some reason. They're going to find occasions to call it, and they're going to call it, including on UI threads. Right? If the user has that domain knowledge that, hey, latency isn't a big deal here, they might even call it on the UI thread, right? So users are really going to have that expectation that you don't have deadlocks. They're going to consider deadlocks a bug, even if you're telling them that they shouldn't be calling this on UI threads. They're going to do it, and they're going to complain to you. And so the key is just really respect the thread that you're on. Don't be calling wait. Don't call result on the thread that you're called on. Don't assume that you're called on a thread pool thread, right? And even in the thread pool, if you're going to block, you'd really rather be awaiting on the thread pool. You don't want to be blocking that thread, even if you knew you were there, because again, that's consuming a thread pool thread for that amount of time. You're being wasteful in the user's thread pool. And so we're going to see more about this deadlock in just a bit. And so really, that's that core principle that library methods shouldn't lie. Be honest. If you're async, be actually async under the covers. If you're a synchronous contract, actually be a synchronous contract under the covers, and or be a synchronous implementation under the covers, and have a core reason why you're exposing that. You should be faster in some sort of core way by being synchronous for you to bother to expose that method. So, that's about being honest about the nature of your method. There's also you having to respect, in other ways, this context that you're called in, right? Context can actually become critical in different ways, and there's different kinds of context, which we'll see. And one of those ways you respect your context is going to be calling this configure await method, passing it false, right? And we're actually going to see how that helps us out with the deadlock that we saw before. There's another thing also called execution context, which is about tracking ambient state, and it's actually a great thing. And we've done the work to wire it up so it actually flows through asynchronous methods, right? The way that it flows through thread creation points and things like that. It's great when you need it and it's convenient, but it can have perf impact. And so you may want to make a very strong decision about, do I want to use this, do I not, based on how it fits your perf needs as an API. And so we'll take a look at these now. So for synchronization context, it's kind of a long name. Who's heard of synchronization context before? OK. A few of you. That probably makes sense, right? It's kind of a behind-the-scenes type. Synchronization context represents a target for doing work. It's actually a pretty simple type. The core method on it is post, right? And the idea is that the post method helps you get back into a particular context, right? It's actually what's being used, or what pipes into these different sync contexts you have for, let's say, WinForms or XAML, right? So for example, in WinForms, the way you schedule work back in a UI thread, that special thread, is you call begin invoke on some control. But if I'm on that thread and I have the current synchronization context and I call post, it's equivalent to getting one of those controls and doing begin invoke, right? So it's a way that I can say, hey, given where I am right now, if I get my current synchronization context, I can put more work there. Or I can hold on to this sync context for later, and I can post work to it. And you think also of like the dispatcher synchronization context, right? This is the one that's used in XAML and WPF, Silverlight. There's one of these for the Windows Store XAML support. And it's like dispatcher.beginInvoke, or for XAML for on Windows Store, it's called invoke async, right? And so this is how I'm going to go schedule work there. And ASP.NET also, as a server implementation, it has its own synchronization context, right? And that's a convenience for you. It lets you have that one request thread and ensure that your different bits of logic that you're scheduling on that request thread don't overlap and don't interfere with each other. And also that you can easily have that work scheduled and stay on that one thread without feeling like, oh, it's easier for me to spin up new threads. No, you can actually await just like you do in UI threads on your ASP.NET thread. And so there's like about 10 more of these. Third parties can create their own for the threading environments that they create. And this is that core way that we're able to resume where you left off. This is the way that the await keyword knows how to put you back where you were. And so when you say await task, when your user says it calling your API, or when you say it as a library author calling other APIs, what happens is we capture, the C# and VB compiler code gen captures the current sync context where you are, holds on to it, right? And that's where it's going to continue later, right? That's where it's going to come back to. When you finally, wait 10 seconds for the download to complete and we come back, we might come back on some other thread, some IO completion port or something. We then want to jump from there back to where you just were, so you can continue writing UI logic and have that trusted environment where you can do UI operations, right? So we save the sync context. Potentially, if there's no sync context, we'll save a task scheduler. That's one of those TPL constructs. We hold on to that, and then when we're done, we schedule you back into that environment, right? It keeps things good. And for app code, right, when you're an application author, this is the behavior that you almost always want, right? I call out to something, I come back, I'm still on the UI. I know I can change button text and update lists and add items, right? Go out, do another download, come back. I know I'm still on the UI thread. I don't have to guess what thread I'm on. This is awesome when you're an app author. When you're a library author, this is actually almost never the behavior that you want, right? You don't actually probably care what threading context you're in, because you're trying to make a general purpose API. Your API should work on the UI thread. It should work on a background thread. You probably don't have UI or background specific work unless you're very specifically making like a UI helper library or something like that. And you don't have to worry about continuously maintaining that and always putting the person back onto the UI thread, because at the outer level, somebody's going to await you. And they await you, and their await is going to put them back on the UI thread. So all along the way in the implementation of your method, there's no reason for you to continuously be scheduling people back onto the UI thread. And so what we provide is this helper method, configure await. It's defined on task, and it takes one bool parameter, whether you want to continue on the captured context. By default, it's true, right? If you don't pass in configure await, that's the behavior you get, which means I do want to post my continuation back where I was. If I was start on the UI thread, I want to go back there. But if you pass in false, what this means is, hey, if possible, let's just continue executing where the task completed. We started on the UI thread, we did some download, we ended up on a Windows I/O completion port thread. Let's just stay there. It's as good a thread as any. We're going to stick around there and do some work. And so if you don't call configure await, you're potentially taking a performance hit, right? Because you're bothering to just keep posting messages into the user's UI message pump. Every bit of async code you want to do has to be another message in the message pump, right? If they're doing one flow, that's fine for them, right? They're doing a handful of asyncs per second. No one's even going to notice it. They take microseconds. But if you're going to do this yourself, maybe you have an inner loop in terms of powering your API, you could be wasting their message pump cycles. And again, like you're being a bad citizen of their UI thread by flooding their UI thread with messages to implement your code. Also, you can end up causing deadlocks, right? And we saw that. We saw what happens if you kind of synchronously wait. The people calling you shouldn't block their UI thread. You can wag your finger at them, but they might have reasons to do it, and you shouldn't deadlock their code. You should at least be able to give them the experience of blocking for as long as you take and then resuming again. So let's take a look at what happens when we do configure await false here. I'm going to switch back into Visual Studio. We're going to go back into our first demo again. And we're going to take a look here at capturing contexts. Now, there's going to be kind of a structure to how I do these kind of perf comparison demos. What we see here is there's kind of two versions. We're going to say we're going to do this 20,000 times. There's one that does flow the synchronization context and does recapture and go back into it here when I'm just saying task.run. And one here when I'm saying task.run and I'm awaiting it, but I'm saying await task.configure await false, right? So doing the same code, scheduling kind of an empty method on a background thread and saying configure await true or false. It's a micro benchmark, but we're going to see what the actual overhead of doing this one thing is. And again, I have one of these Windows Forms apps, so I can get a UI thread. And you see that part of the general pattern is we're going to have this kind of like warm-up code here that's going to at least run each method once to kind of make sure it's JITted and we're not paying that cost and that's not confusing things. And then once we've done that, we're going to go run this 20,000 times and run that 20,000 times. That's what we're going to do. So let's try this out. So I run this here. I hit run. It's running. And we see that when I was flowing the context back and I was kind of resuming on the same UI thread over and over again 20,000 times, it took 0.6 seconds, right? So it's still not very slow. It's like each one is sort of still on the order of a few microseconds. But it adds up when I have 20,000 of them. And without it, you see it's 0.05. So it's kind of an 11x slowdown. Again, this is a micro benchmark. All the benchmarks you're going to see are micro benchmarks. But it does mean there is a sort of non-trivial overhead to you constantly going back, right? If you're going to do like 5 or 10 awaits inside your API, it doesn't matter, right? And just like it doesn't matter for app authors, right? But if you find yourself knowing I'm going to have to do a bunch of processing, it's going to have to be asynchronous, and I'm going to be doing this in maybe some kind of loop, you want to consider putting configure await there. And really, your habit should be, if you're a library author, if you're writing a library method, you almost always, when I say, hey, await T, you want to kind of just, as a habit, say configure await false. Because there's almost no cases where you do really have to come back and jump back to the thread where you just were. You'll know those cases when you have them because you will be somebody writing UI code. OK, so this is configure await. And if we go back to the slides and take a look, like, we saw that it helped with perf. It actually also helps when you have deadlocks, right? That deadlock that we saw before is going to be assisted by us doing this, right? And so this is basically the same kind of example. I have a button click. I'm awaiting some asynchronous method. That asynchronous method is going off doing task.run, right? This is the code we wish users would write. But sometimes users are going to write .wait, right? And we have to be able to handle that without deadlock. And so let's say they do this. Well, do work async, what happens here? They go into the button click, and we're going to call do work async on the UI thread. Okay, sounds good. We go to do work async, we get to task.run. That's going to schedule work to go off into the background, run it in the thread pool, schedule an item. It's going to do that work, whatever. We're going to come back. We're going to get to the await. Remember that await means I'm kind of returning from my method and bouncing back to my caller. So I return to my caller. Actually, but before I return to my caller, await first captures the sync context, right? I capture it, hold on to it, hook up that continuation, and then I return. And I return, and then you see the first thing I do with the task that was returned from that asynchronous method at the await point is wait on it. So now the UI thread is blocked. It's going to be blocked until it gets a signal that says this task is completed. So now I go back into the library, like maybe 10 seconds elapse, however long this synchronous stuff in the background thread takes to finish. It's like, OK, cool, we're done. And then, like good, since then the async support that's in the language says, cool, we captured the context. We're now going to schedule the rest of do work async back on the UI thread, because that's where we were. That's what we're supposed to do. So it says, OK, cool, let's post this back to the UI thread as a message. It adds a message to the UI queue. Unfortunately, we're never going to get to that message because we just blocked the UI thread. The UI thread is waiting for a signal from that message's calling method, the one it's going to call into, to say, oh, cool, we're done, and unblock the UI thread. But we're never going to get there, so we're never going to unblock the UI thread. Each part's waiting for the other part, and we have a classic deadlock. So what can we do instead? Well, we can't change what the user is going to write. They're going to do whatever they want to do. We can change what we do on our end by adding configure await. So you see, we now added configure await to our API. We're awaiting task.run, and then we're calling configure await before we await it, right? What that does is it means that when we await, we're no longer capturing the synchronization context. We're just hooking up this continuation to come back and call console write line there. And we're going to do it in whatever thread we happen to end up on, which is going to be that background thread where we did all the work. We're just going to stay there. And so that means that you come back, the UI does block, so the UI is going to be blocked for that time. There's no avoiding that. You're doing work synchronously on the UI thread. But when we actually finish and we post back to the UI thread, or we would post back to the UI thread, we're not doing that anymore. We're just going to complete where we are. We're going to continue running. And we do that console write line. We finish do work async. The method exits. We signal completion. And then that means that the UI thread picks back up. We haven't had a deadlock because we've operated and we've finished our async method, our library async method, on a thread where we actually have the ability to continue on. And so if you're a library implementer, you should use configure await false to let you improve performance and help deadlocks, help avoid deadlocks, right? In the user code. If they're going to actually go and block on your method, you don't want to screw them over, right? So actually, before we go on, I do actually just want to show, just so we can prove that this does work. I'm going to go back to the store app we had. That store app, the Windows Store app where it hung forever, well, we're not going to change the user code. We can't affect what app authors are going to do with our library. But I can come here and say in foo async, I'm going to say configure await. And this is going to be the thing now that I'm awaiting. I'm going to say configure await false here. And so now when I run this, it runs, and I click the button, and it does stay down for 1 second, but then it pops back up, right? So if the user's going to call us on the UI thread, they're going to get delays, right? That's why we have all the asynchronous APIs we're exposing. But we can prevent deadlocks by using configure await inside our API implementations. So there's actually one other interesting kind of context that's worth talking about, and that's execution context. And execution context is this idea of having this ambient container for having sort of information that applies to an entire async operation that's flowing through. You can think of it sort of as an async aware or a thread switch aware thread local storage. So like the danger of thread local storage when you do that is, well, if I start operating on this thread over here now, well, my thread local storage is over there and I've lost it, right? This execution context is something that's explicitly flowed when you switch threads, when you say task.run. When you say new thread, when you say queue user work item, all these different ways that you kind of move between different threads or spawn new work, these are execution context aware, and they have been for a while. And they go and take that execution context and put it on that new thread. And people use execution context for all sorts of things, for knowing what your current user is, your NT user, especially if you're doing like impersonation or something. You might remember the activity ID if you have kind of an ambient activity. And so you want to use this kind of ambient context. It's very convenient. And we make sure that we flow it correctly so we don't cause security holes, we don't cause other issues. So we're internally optimized here for this like default context, right? Assuming that you didn't change it is actually a reasonable assumption because most apps don't have a need to set any of these ambient kind of things that affect it, right? And for example, like if you're setting correlation manager dot activity ID, this is some API you can set. If you set it, it's going to set up some of this ambient context. We'll flow it correctly everywhere. But we assume you don't, right? And the first thing we do when we call one of these methods, when we do an await, we make sure, hey, is the execution context still in its default state? If it's still in its default state, we go to a fast path. We don't even bother flowing it. We just know we're going to come back. We're going to just dump you into the default execution context. We're good to go. If we notice it's not in the default state, then just like the sync context, we have to start handling the execution context. We have to hold on to it. When we come back, we have to make sure we kind of reestablish all of that to make sure that you're good to go again. So if you're writing a library and you want to have the best performance for your library, you may want to consider avoiding execution context if it's not necessary for your needs, right? Now, if you're doing things that involve NT impersonation, if you're doing any of the things that really need execution context, then by all means, use execution context, right? But if you're kind of using it just because, hey, it seems a bit more convenient, I'm going to have this kind of ambient flow, I'll have my users set up something, and it's going to flow into all my async methods automatically, that can be convenient, but you want to be aware of the performance cost that it has so you can make that trade-off yourself and make a good decision for your API. So let's take a look at how much that cost is. If I go back to my app, I'm going to go to the perf demo app here, and we're going to go into this other demo. And this one's going to do 100,000 iterations, and you see here I'm having this do-work async method. It's just doing async or await test.yield. Test.yield is just this simple helper method. All it does is kind of lie to the async infrastructure. It says, well, I'm not complete, but then immediately it says it is complete. So it gives the message pump a chance to breathe, and it kind of just, almost like scheduling like a zero-length delay. And so we're going to do that, and it's going to represent this sort of very short asynchronous work. And what we're doing here, we're saying here, call context.logical set data. This is one of those methods that goes and puts something ambiently this is a type of execution context. And this is going to flow automatically whenever I have an await or a dot wait or any of these kind of methods that do this stuff. So here, I'm saying I'm going to wait on this one, and I'm going to wait on this one, and we see that this turns into sort of 0.27 versus 0.17, right? So there is this kind of 50% difference based on whether we have to flow that, right? Now, this is true here when I'm flowing this synchronously across awaits, right? But even though I'm waiting here in my app, right, the person's trying to do like sync over async in their app, there still is that kind of underlying cost. The cost of flowing it across my await task.yields inside my API, and assume that was any sort of like really short work that I wanted to do, it does kind of add up, right? And it was about a 50% overhead. So you might be willing to live with that overhead for correctness if it makes your API way easier to use, right? But you want to be careful. You want to make sure that you're making that trade-off wisely, that you're actually making that as an explicit decision. So just as something to watch out for, if you design an async library around either you modifying execution context in your implementation or what we saw here, expecting the user to modify it and then sort of having it flow into your method, maybe you'd be poking at it, that kind of defeats some of the built-in optimizations we have around async methods. And so there is going to be a performance trade-off there. It's up to you to judge if that's worth it. So this one principle here around being a responsible library developer, know that library methods can be called from various environments. Know that context is critical, right? Like either sync context. If I care, am I on the UI thread? Am I on a background thread? Each one of those has some different sync context. I could be in ASP.NET. I could be anywhere, right? If you want to operate in all the different sync contexts of the world and UIs and servers and background and foreground, you really want to then just try to avoid having any dependencies on the nature of the sync context you're in. And the way you do that is by using configure await false. And also, as we saw with execution context, see if there is some other way that you can track ambient state. There may not be. It might be the best option for your API, but make that decision explicitly. So kind of the last thing we want to go over here is actually just digging deeper into where these perf gotchas come from. Like, why are there some of these issues with async perf when I have like a really tight loop? What kind of async APIs should I expose? For me as a library author, right, it might be tempting for me to just wrap every single synchronous method I have with an asynchronous method. And maybe I would go down and actually have a deeply asynchronous implementation all the way to the bottom. But if I have like sort of a method that's like getting a byte, do I want read byte async, right, on my API? Like, it seems like it could be very convenient, but if I'm getting a million bytes one at a time, there could be some overhead there, and that's what we're going to look at now. And so it's about making what we call sort of chunky APIs versus chatty APIs. When you make async APIs, you want to kind of think of broader chunks of data that you want to go back, which means that that overhead is basically negligible. And we're also going to see some cool things around what we can do to actually optimize in the synchronous cases and in async methods when you actually have maybe a cache hit or something, right? What you can do to make that fast and how you can actually implement these caches efficiently. So sort of just to kind of step back, we think of how we have methods that are running, synchronous methods that are running. This is really what we've been used to for years, for decades, right? We know that synchronous methods inherently are cheap. You all have written synchronous methods before, right? That's what everyone here is used to. And from the OS up to the platforms like the .NET framework, up to all the APIs that are being called, that are going to make assumptions about the fact that they get inlining and all this stuff. All of these are optimized around the notion that sync methods are super fast. And we've had decades of optimization to make that happen. And it means that you feel like you can refactor your code at will. Like, oh, I want to take these 2 lines of code and put them off into another method, right? And that's something you can do that's fine. And inlining will fix that. If you look at the IL that this method, this synchronous method, emits, right? Now, IL is not the best way to estimate performance, like number of lines of IL. But especially if you're going to call console.writeLine, it's going to go off and do like string stuff. It can end up doing string formatting and locale things. And so, it's not the best way, but we're going to use it as an approximation, at least of the contribution this user code is going to have to it. And so you see very simple mapping, right, from the code that you wrote to the IL, and it's going to go down and be really optimized inside the CLR. You're going to get a super fast implementation there. Now, for async methods, the story is a little bit different. So this is the body of the async method when it's compiled. This basically has the same body. It's printing hello world. But already the plumbing that's there to make async methods work is starting to become more appreciable inside the code, right? There's still calls here. I'm still having the same return value. Actually, in this case, I'm returning task, right? And you see I'm doing different things. But mostly this is like infrastructure. You don't have to squint and read this, right? You can just appreciate how much code it is, right? I'm making an async task method builder. It's kind of a state machine. I'm going to be calling this move next method here. This is how I power the state machine. But this move next method is actually generated, right? This move next is where the body of my code is. You see the console write line is not actually in here. It's in that state machine that's going to power async and make sure I can pause and resume. So what does move next look like? So yeah, exactly, right? This is the implementation of move next that I have. And I notice if I look deep inside, right, there's the nugget right over here. This is the code that I originally had in my synchronous method, right? It's still there. It's printing hello world, and it's going and returning, right? But all around it is the plumbing to make sure things work. And you see what's here. There's a try-catch, right? So half of this code isn't going to be run in kind of the successful case, but we're still paying the cost to set up a try-catch, right? Because we have to be able to route those exceptions into the task object. And even in the case of successful completion, you see there at the bottom, there's set result, right? Well, we can't just return the task. We have to have made the task, and we get to the bottom, we're saying, okay, this is now completed. We need that infrastructure that's going to go and mark it as being complete. So you get all sorts of awesome convenience, right? And you get to write methods that probably would be too complicated to even reason about if you didn't have the async support. We've done that in .NET 4.5 around some of the XML support. Previously, it was beyond sort of human ability to go write these async XML APIs that would go and dig deep because they call into like 10 levels of nested stuff based on all this different XML things you might be having. It would be horrendous to rig that together, and it was super easy to do with async. So it does unblock you to make awesome APIs, but you want to know that there are potential performance costs that you could have to deal with here. So just to get an idea, and sort of another one of these micro benchmarks to say, what is that actual measurable overhead for an async method? We're going to go back in, and I'm going to come back here, and we're going to sort of look at an empty body. And you see that I have the same implementation here. We're going to make sure there's no inlining, and I have an empty body, and I have an empty body that is now async void. You see the only difference is that we put the async modifier here, and that async modifier means that we're going to get that kind of state machine implementation. But you notice we're not doing anything. We're just going to have the plumbing. We're going to isolate the cost of that plumbing. And we're going to do this here 10 million times and do each one, right, and measure it 10 million times. And when I run this, we see that I was able to run the synchronous version 10 million times in 0.02 seconds. So computers are pretty fast these days. I can do that a lot. And the async version, right? The async version, I had this plumbing that had to be there. We saw what that was, and it took 1.2 seconds. Now, remember, it's running 10 million times. So that's on the order of about 1/10 of a microsecond for the async overhead. So if I'm doing this like 100 times, nobody is ever going to notice that, right? And that's really where the key is, right? I use async, it's great if I don't put it in my tight loops or whatever. Even if I do, if I'm going to run it a few thousand times or 10,000 times or even 100,000 times a second, it's probably perfectly fine. But if you have such tight, small code that you're going to be going over a super inner loop of an inner loop that's going to run millions of times, you potentially want to avoid having awaits in there, right? That you're going to be doing millions of awaits per second. That's where this overhead is going to start to add up and be an appreciable chunk of the work that you're doing. Oh, actually, one even more interesting thing that's to see there, just so we can even isolate exactly what that looks like, I'm going to go into my empty body version just to slow it down. I'm going to put some work in here, and I'm going to say, all right, just do sort of an empty for loop. And it's going to loop 250 times. And when we run this now, I just sort of put some work into my sync method. Now they're about equal, right? So if you want to think about how much it is, it's sort of like 250 spins through a for loop is about the size of the async overhead, right? So we shouldn't be scared of doing loops that have 200 iterations, right? But we want to make sure we're not doing that inside of another loop 10 million times. And that's the lesson there. So async methods, when you generate them, they've got a try-catch. They have calls into these framework helper methods. They access fields instead of locals. The trick, the way that you actually have a local, like int x, right? I want to access it after the await. How do we get back there and save that local? Well, it was shoved off into the heap, right? So there's some copying in and copying out that's going to occur. So that overhead isn't terrible. Remember, it's about 1/10 of a microsecond on this laptop. But we still don't want to encourage people to be super kind of hyper chatty with our API and call us millions of times, right? When we're, as library authors, designing our interface to the outside world, we want to see where these natural points of chunking are. Can we return an entire row at a time rather than like bytes from the row or things like that? Or can we return a chunk of rows if we know we're going to return a lot of data, right? And again, this is one of those cases where you want to measure. If you're only going to be returning a few hundred per second, it's fine for people to await you 100 times, 1,000 times a second. But don't encourage a pattern where people are going to be awaiting you millions of times a second. And so you really want this different mental model, right? You want to think hard before you end up going really fine-grained with the APIs that you're producing. Now, the one catch here and the one thing to remember is that all of these costs we're talking about are not particular to the async implementation we have here in the compilers, right? If you are already exposing an async API, maybe you're one who's out there manually making begin-end methods today and paying that pain and that cost of creating asynchronous APIs, what we've done here, we believe, has similar or probably less overhead to any manual thing you're kind of rigging up today if you've handled all these cases correctly. Because we've been able to go internally and optimize the COR, optimize the .NET task type to have fast paths for all of these things. And so it's not that asynchrony itself, or that this async implementation, the await keyword itself is slow. It's that there's some certain inherent overhead on today's processors, on today's platforms, to doing asynchrony. And so if you're going to do asynchrony, probably async await is the fastest way to do it. And typically, even there, the overhead is going to be negligible. But for extremely chatty APIs that go millions of times a second, that overhead might start to add up. So sort of before the last set of demos, we just want to go into one kind of quick foray off into the garbage collector, which is really where a lot of the cost from making async libraries and making async code actually comes from, right? And we all know .NET is managed. It has a garbage collector. This is one of the key benefits of writing in a managed language. But that management doesn't come free, right? Allocating objects has a general cost. Now, that cost is kind of all chunked up at the end, right? Like when I allocate, it's super cheap. It's basically some pointer manipulations. I have a new object there. That's almost free. But when I finally do a GC, all of that savings from having cheap allocations finally comes and hits you all at once, right? And so if you're trying to play nice with the garbage collector, you want to help avoid garbage collections whenever possible, minimize the number of garbage collections you're going to cause, right? So if you have a bunch of big objects you're defining in your library, that's going to cause more garbage collections and longer garbage collections for your app authors. If you're making huge objects, right, those objects are just going to take up a bigger chunk of these garbage collector segments. That's going to cause more garbage collections. And allocations have a global effect. It's kind of like the thread pool when we talked about that before, right? There's really one set of segments that you're going to have in the app. The app author has this pool of memory that he's operating in. You're swimming in that same pool with your library. So you want to play nice with the garbage collector so that you don't actually mess with anything else he's doing that might be allocation intensive. So what you want to do is you want to avoid unnecessary allocations, and you want to avoid bloating the objects that you're going to allocate. And this is true in general, right, for any kind of method that you're defining in a library. But for async methods, there's certain unique allocations that show up. And so, for example, if I have an async method, well, what's one of the things I might have? Right? Well, I need to have this kind of state machine. You saw kind of the implementation for a state machine. And you don't have to squint and see what's on here. But the idea is like, all right, well, I have a state machine to track the flow of my async method, and I have to know what state was I in, so I know where to kind of jump back to in the delegate. And I also have to have that task builder. I have to have, something I can call move next on. This is my state machine, and it's a class. It's going to be shoved off into the heap, so it can survive, even though I've kind of pulled back and gone back in. Or it could be a class. We'll see what happens there in a sec. The completion delegate, well, I need to allocate this delegate. Delegates in .NET are heap objects, and so I need to allocate the move next delegate, which is what powers this. It's how it remembers, hey, when I'm done, I'm going to jump back to this point in your method. Well, the way it jumps back in is by capturing a delegate that lets it do that. And remember that your async method is going to return task, or it's going to return task of t. And that task object being returned is a heap object. It's an object that's going to be there. It's a task as a class, right? It's not a struct, so I'm going to have to allocate this and return it. So potentially your async methods have those three allocations that are going to be involved. And potentially if I was going to call into one method, to another method, to another method, and then come back, every time I called an async method, I'd have three allocations I have to deal with. And that could really add up and really give you a pain when you're dealing with the garbage collector. So the key, and the saving thing for async, the core principle, the performance principle that makes it so async methods don't have that terrible cost, is the fact that async methods start running synchronously. And this is key to understanding asynchronous performance, especially as a library author. There's an asynchronous fast path that comes in, right? Remember, you start running your async method, you're synchronous as you're coming in. And maybe your method is like a cache method, and the reason you're asynchronous is because you might have to go out to the network, and you might have to download something. But 99% of the time, let's say you don't have to download something, right? You're just going to look up in your cache, ooh, I have a hit, and then I'm going to go return that data back. If you make it all the way to the end of your method without actually needing to be asynchronous, without actually having to go off and pause your thread, then you actually can save a lot of these allocations. So if you look at what await async actually produces, we say, all right, well, if the awaiter is completed, right? Async or awaitable objects have this getAwaiter method. And so the first thing that we check as well is the thing we're awaiting already done, right? Are we awaiting something that we say, oh, I want to go get this file. Windows comes back and says, oh, I've got this in my IO cache. Here it is. Nothing was ever asynchronous, right? Well, fine. Then I'm already done, and I just kind of continue executing. We skip this whole block where we were saving state and resuming it and putting things in or out of the heap. We just keep going. We call get results synchronously, and we hand it off. We were never actually asynchronous. And so because async methods can complete synchronously, we can do optimizations, right? Remember that state machine we looked at? It was a class there. Well, we don't actually implement state machines as a class. We implement them as a struct. And the idea is that, well, as a struct, we can put it on your stack, keep it there, use a stack memory. You don't have to worry about allocating heap objects and causing garbage collections. Only if you really have to be asynchronous, we then take that struct and we kind of box it into the heap, right? Only then do we do that. Otherwise, we keep it on the stack. It never causes a heap allocation. We also wait. Remember that delegate you see in there? There's kind of a completion delegate that's going to be registered to the awaiter. We're going to say, hey, on completed, call this completion delegate. That's what kind of jumps us back into our async method where we left off. Well, if we never have to be asynchronous, we never have to make a completion delegate because we're never calling on completed. So we wait to do that until the last moment, until we really have to. And the last part, though, I mean, my method has to return a task, right? If I have an async task method, I got to return a task. So it might seem that that last allocation is kind of unavoidable. Where's the task going to come from? But we're actually pretty aggressive about trying to use cached tasks in those cases, right? And we'll see what that means exactly, right? Many async methods can complete synchronously. This is that key to asynchronous performance. And when you're writing an async API method, especially when you expect to be called very often, maybe you're writing a cache, this is the key to actually getting async performance out of something, right? The fact that you want to have a synchronous path through your method that can get to the end, that can get to a return statement without actually having to do any awaits, right? If you can pull that off, and maybe 99% of the time when you have a cache hit, then you benefit. Now, we potentially can't always eliminate that third task allocation, right? The framework caches some common tasks. Like it caches this task here. Like if you look on the non-generic task, foo async, right? A non-generic task can be in one of two states. Either it's not completed or it is completed. Maybe it's like an error or something, right? But if I make it all the way to the end of the method and it's already completed, it's just a task that when you ask it, are you done, it says yes. All of those tasks are equivalent. There's no point allocating a new one all the time. So if I have a task that is already completed, we might as well just store one of those. And every time you make it to the end of a non-generic task method that's async, we just give you back that cached already completed task, right? So we don't have to allocate those. We don't have to allocate task of bools. There's only 2 task of bools you could have that are already completed, one that's false and one that's true. So we just make those in advance, and we have them to give back to you. And the same for task of object. Like if you want to return null, we already have a task, or we cache one at the time that you make it, right? And then we return that back to you. And these are good because a lot of people use these as sentinel values. Like you might imagine some sort of moral equivalent to like a try, get, foo method. And those tend to return bool. Well, if you return task of bool, then you can have a very optimized path in the case where you're returning true, if you're going to then kind of do some assignment there. So you can decide to cache additional cases yourself, right? We don't actually cache more than this right now in the framework. And you wouldn't want us to cache more than this, right? Think of a lot of the task methods you have that return strings, that could be giant strings. You don't want us to keep a cache alive that's going to kind of hold on to those, right? Like, remember the maxim that like a cache that doesn't have an expiration policy is really a memory leak, right? You don't want us to be doing that work for you. We don't know what task we should be caching, but you might, right, based on your domain knowledge. And so if you look here at memory stream read async, right, this is that read async implementation we talked about before. It's just going to call the synchronous read method, right? It does some checking on the cancellation token first to be a good citizen, and it just calls the synchronous read. And this is a perfectly fine implementation because that read call is going to be super quick. And so the thing is, the read async call here returns task of int to say how many bytes it read. And you wouldn't want the framework to cache every task of int that happens to flow through this method. But if you look at how people commonly use a stream read, you're probably doing it in a loop. You're going to read 4K, another 4K, then another 4K. You're going to constantly be reading some constant size, right? Almost always, the count you get back from this is going to be the same as the count you just got back last time. It's going to be true all the way up to the end when you get your little like fractional count at the end of the stream. But usually it's going to be the size of the buffer that it's operating on over and over and over and over and over again, maybe 1,000 times if you have a big file. And so what you can do, if you really want to squeeze out that perf inside your implementation, you could say, well, instead of directly making an async method, and especially here, since I'm just calling this synchronous method anyway, right? And you don't have to squint at this. We'll see the code in VS soon. But I don't have to make a real async method to do this. I could just say, fine, call read. If I get back some number of bytes, and it's the same number of bytes I returned last time, well, I held on to that task from last time. I'm just going to give you back the same task again. It's an already completed task that says, I returned 4,096 bytes. And I can just keep giving you exactly the same task object over and over again to say I have my data available, because I'm a memory stream. I always have all my data available, right? And I'm avoiding that repeated allocation of that task to say, yes, I have another 4,096 bytes for you. And that's this kind of core code that you see here. So we're going to go to the demo, and I'm going to show you this in code. And we see here, and this is basically kind of a quick async comparison. I have memstream1 and memstream2. I'm going to track garbage collections. You see I'm tracking kind of Gen 0, Gen 1, and Gen 2 garbage collections for these 2 different async API implementations. And for memory stream 1, that's that simple original case we saw. Just come in, call the synchronous read, and you're done as a simple async method. For memory stream 2, we're doing that trick that we talked about, where we say, all right, well, let's do the synchronous read. Let's see, well, we have this mLast task where we save the last task that we gave back. If the result from the last task, which is an int, right, equals the number of bytes we read this time, just return that last task. It's already completed. It represents the task we want to give back. Just give it back, right? You notice that this isn't an async method. This is us kind of just spinning up our own tasks to return because we decided we really want to optimize this method. We did some profiling. We figured out this can be a choke point. We want to optimize this. And so I just give back that same task if I can. And then, in the case where I don't happen to have the same task, if it's the first time or it's that last time when it's going to be a different size, then I call task.fromResult. It's just a simple helper method that says, take the value and just return me an already completed task that will spit out that value when you ask it what its return value was. And so I do that. I give that task back. And there's some other code for exceptions and cancellation token, but this is really that core. It's not that long to write. And so I have that. And let's actually see. If I run my code, I see that for memstream1, I'm getting kind of 14 Gen 0 GCs running through that a bunch of times. And for memstream2, I'm getting 4, right? So I've eliminated 10 garbage collections from my user's app by just ensuring that I'm not spinning up thousands and thousands and thousands of these equivalent tasks that all just say, here's 4,096 bytes back. Right? I'm able to respect the garbage collector, respect the environment I'm in by keeping one of those tasks and constantly reusing it. Oh, actually, even one more thing here. Like, you might wonder, do I have to go implement this myself if I did memory stream? Well, if I take memstream 2 and actually just replace it with memory stream, you see that memstream 1 probably still has about the same behavior. It's 14. And memory stream 2 has a bunch of optimizations even further that we've been able to do, plus it's engen, right? It has more inlining, more aggressive inlining it can do. It can optimize some of this stuff. It's able to get away with actually no allocations, or no Gen 0 garbage collections, not enough allocations to matter. And so using domain knowledge that you have about the nature of your API can let you decide to cache tasks in a way that will lead to improved performance for your callers. And in the .NET framework, internally, when we used this, we were able to use this fact to dramatically improve the performance of buffered stream and of memory stream, which have this characteristic. And so the one last really quick thing I want to show is we've talked here about creating a task, creating a cache, but you can actually be even more aggressive when you're caching, when you're doing this kind of async caching in your library, about caching the right thing, right? You know, you don't have to understand this code. It's just the super simple kind of string-to-string dictionary code, right? I want to cache downloads I do. I pull in some URLs. I want to cache the string that I download, and I want to make sure I don't have to download that again if someone asks for the same URL. And so I write this code. It says, hey, if we have a cache miss, go fetch it. Otherwise, return it from the dictionary, and that's fine. But you notice the one thing here. This is an async method. So every time that this method returns, I'm going to have to make a new task of string. Even though I cached the strings, I cached the actual logical return value from my method, I still have to make a new task of string every time. And so I'm suffering that allocation each time I do that. So the trick here, if you're writing a library that's going to do this kind of caching, cache the task of string, right? Make an outer method that kind of calls your async method. You still have the core of your logic in the async method. Do that, but then have this outer method that's going to actually take the task that it got back and cache that, right? And make that the thing. And then if somebody calls you again and you notice the URL is the same, just give them back that same task. And you don't even have to allocate the task again. We're going to quickly jump in and just see the difference that that can make. If I go here, you see I have, in my code, I have two dictionaries. I have one that's going from string to string. That's the one that actually just only caches the strings. And I have this one here that caches task of string. And I'm just going to compare these two implementations, this one that does the string caching, this one that does the task caching. And you don't have to worry about sort of copying down how the continue with thing there works. You can go look that up in the slides later when they're posted online. But I'm basically going to be comparing these two implementations. And we see that when I'm caching the string, it takes me 1.8 seconds to go through and do, I can see exactly how many these were. This was 10 million iterations, right? So doing 10 million iterations, talking to my cache, the first time it did a download, the second time it was already there, and so on. 1.8 seconds. When I was caching the tasks, it was 0.6 seconds, right? So the only difference there is what I had to allocate those tasks each time. But I was allocating them when they were allocating above a certain size, or garbage collections. If you want to help avoid those kind of garbage collections in your user's app, make sure you're caching the most aggressive thing you can, which is that task object. Yeah, and so yeah, whenever you have the opportunity, if you notice yourself in an async method making a cache of t, think if you can make a cache of task of t. And so really that's that kind of last principle, right? You might be used from code that's perf sensitive, right? If you're used from code that's going to call you 5 times, it's going to do some quick thing on a UI thread, doesn't matter, right? But somebody might decide to call you 1,000,000 times. They might have a very aggressive use of your API that they want to do. And if you're encouraging that kind of pattern with the design of your API by returning one little nugget at a time, and people are going to have to call you a bunch of times to get things done, they might fall into these perf traps, right? So if you can, design your async API to be kind of chunky. Give a bunch of rows, give a bunch of objects back if it makes sense for your API rather than being very chatty. And then know that we're optimizing for you those kind of synchronous cases, right? And so if you can get to the end of your method synchronously when you have a cache, do so, right? And make sure that you optimize for those kind of patterns. So when people do want to call you a bunch of times, they're not paying the cost of that thread switching. They're able to have that fast path in that 99% case when you have the cache hit. And if you are doing a cache, make sure you're caching tasks, not just the raw objects, so you can squeeze out that last bit of perf. And so these are those core principles. Library methods shouldn't lie. You can be called from different environments, and respect the fact that the people calling you are going to be dealing with perf-sensitive situations sometimes. All right, and so that's the talk. Thank you. We have some other talks that I've given here. If you want to go back and review, this is the last async talk that I have for this week, but we have all these talks that are going to be posted online, from how you do things in Windows Store apps to some of the core async tips to this talk around async libraries. And you can go back and revisit this if you want to see how we did some of those tricks, such as task.continuewith. Thank you.